Okay, so what we saw in the previous lecture was how to calculate the local ring of an affine variety at a point. Okay, so the result was that if x is an affine variety and p is a point of x, then the local ring of x at p is given by taking the localization of the affine coordinate ring of x at the maximal ideal inside the affine coordinate ring of x ax. This maximal ideal MP has to be you have to localize ax with respect to MP, and the local ring that you get can be identified canonically with the local ring of x at p. Okay, now what I am going to do now is I am going to try to do the same thing for a projective variety. Okay, and just as in the case of an affine variety, the local ring is given in terms of localization of the affine coordinate ring. In the case of the projective variety, it will be given by suitable localization of the projective or homogeneous coordinate ring of the projective variety. Okay, so let me state that. Okay, so here is the theorem. Let y be a projective variety let p be a point of y. Okay, then OYP, the local ring of y at p, is isomorphic to the homogeneous coordinate ring of y localized at MP. Okay, this is an isomorphism as K algebras where yeah, I need to so I need to localize and also take this degree 0 part. Okay, so where Sy is the homogeneous coordinate ring of y, MP is the ideal generated by functions in Sy which vanish at p. And this notation means take the degree 0 part of the graded ring. Okay, so let me explain this. So you see the situation is you have y y sitting inside as an irreducible closed subset of projective space, okay, and then of course you have the homogeneous coordinate ring of the projective space, which is just the same as affine coordinate ring of the affine space above, of which the projective space is a quotient, of course a punctured affine space and this is going to be k x naught etc xn polynomial ring in n plus 1 variables, okay, and the homogeneous coordinate ring of y is just the quotient of this by the ideal of y. Mind you, y is a closed subset of projective space, so it is given by a homogeneous ideal, okay, and the homogeneous ideal is going to live in this polynomial ring, which is a homogeneous coordinate ring of Pn. So this is, so Sy is just S of Pn mod Iy. Iy is simply all those Iy is just it is the ideal generated by all those homogeneous polynomials which vanish on y, okay. It is a homogeneous ideal because it is generated by homogeneous elements, and therefore this quotient, because you are taking a graded ring and you are going modulo homogeneous ideal, the quotient also becomes a graded ring, okay. So Sy is also a graded ring, okay, and the gradation is simply given reading mod Iy, right. Now the situation is, how do we get this thing. So we use the following facts which I said in the previous lecture. The first thing is, to calculate the local ring you can go to an open subset, okay, that is one fact. The second fact is of course that if your subset is affine, then you have a formula for the local ring. So what we are going to do is we are going to do a very simple thing. We are going to take you are going to take the point P of y, and of course the point P is going to lie in one of the ui's, being the open subsets of Pn. There are n plus 1 of them, each one of them isomorphic to an, the affine n space. So P is going to lie in one of them. Then what you are going to do is we can just intersect, so P will lie in y intersection ui, but y intersection ui is an affine variety, okay, and therefore it is easy to, we know by the previous theorem, we know what the affine local ring is, and we also know that the local ring that we get will be the same as the local ring of y at P. So this is what we are going to do, okay. So here is a, so let me draw a diagram. So there is a diagram like this. So I have the following situation. So I have Pn, I have ui, okay. So P, so let me write here, P is in y, which is contained in Pn, which is union I equal to 0 to n plus 1 of ui, where ui is the set of all points lambda 0 with homogeneous coordinates lambda 0 through lambda n, such that lambda I is not 0, okay, and so this how, so P belongs to u I naught for some I naught as without loss of generality, okay. So let me so let it be like this. So we do the following thing. So I have this u I naught which is isomorphic via the morphism phi I naught with a fine n space, okay, and we saw this in the lecture before the last lecture. No, you're right, I should start with 0 and end with n. Yes, yes, thank you. Yeah, it should be u naught through u1. There are only n plus 1 of them. Thank you. Yeah, so it should be I equal to 0 to n. Okay, thank you for that. So yeah, so you see this, we have already seen that this isomorphism is given in terms of rings in the following way. So there is a phi I naught, so this phi I naught induces phi I naught star, which is given by pullback of regular functions, that will go from the regular functions on an to so if you have a morphism, regular function on the target will by composition of this morphism give you a regular function on the source, okay. So I will get regular functions here to regular functions here, so I will get this to this, but you know, of course this is just because this is affine, this is just a of an, and that is identified with k t1 etc tn, these are the coordinates on the an, okay, and ou is, as we showed in a lecture before the last lecture, it is just the coordinate ring of Pn localized at xi, and then you take the degree 0 part. So this is so here it is I0, so here also I have to put I0. Okay, so this is something that we have seen, and we have also seen what this map is. We also have this, we know what these maps in these two directions are. So the map in this direction is given by, well, you give me a polynomial f of t1 etc tn, then the map in this direction is given by homogenization. It's given essentially by homogenization and dividing by by xi to the power of degree f. So it's going to be xi degree f times f of x, so this is xi naught to the degree f x0 by xi naught dot 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 xn by xi naught and then divided by xi naught to the degree f. This is how this map is given, okay, and of course when I write like this I mean forget xi naught by xi naught, alright, so that you have only n of them, because there are only n variables that I can fill, that I can substitute for, okay. So this is how this map is given, and we also know what the map in this direction is. That is also something that we have seen. If you give me any element here will be of the form g of x naught etc xn, this homogeneous polynomial of certain degree, okay, divided by xi naught to the degree of g. This is how an element here will look like, okay, because you are localizing at xi naught, okay, which means you are dividing, you are inverting powers of xi naught, but then you want the degree 0 part, which means that the numerator degree and denominator degree should be the same, which means that the numerator should be first of all a homogeneous polynomial of a certain homogeneous degree, and the denominator should be the same degree as the numerator, so the denominator should be xi to the power of, to that power which is equal to that degree of the numerator polynomial. So it's going to be like this, and what you're going to get here is just simply, you know, you substitute xi equal to so you just substitute so you divide, you take x naught etc up to xn divided by xi naught, okay, and omit the xi naught by xi naught term, you get n terms, and you just you just no, that was a map in this direction. So what you do is you just put xi equal to 1, okay, and then for the remaining x0 to xn leaving out xi you put t1 through tn, that is what you do. So the map in this direction is t1 blah 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 1 tn, where this 1 is in the I0 place, okay, so that you now get, you have substituted for n plus 1 variables, and of course you essentially you are substituting xi0 is equal to 1, okay, so the denominator is going to just vanish, I mean it is not going to vanish, I mean it is going to be 1, so it is not going to show up here, right. So this is how this isomorphism is. This is the commutative algebra version of what is happening here in geometry in terms of regular functions. Everything here is in terms of regular functions. Now what I am having is I have inside Pn I have this y, which is a closed subset of Pn, irreducible closed subset of Pn, and then I get this y I0 which is just intersection of this is just intersection of y and du I0, okay. So what happens is that y I0 is an irreducible subvariety of u I0, because you see y is irreducible closed, y is first of all closed in Pn, therefore y intersection u I0 is closed in u I0, so this is certainly a closed subset of that, and then this is y I0 on the other hand is also irreducible. Why? Because y I0 is y intersection u I0, which is an open subset of y, and an open subset of something that is irreducible continues to be irreducible if it is non-empty. Therefore mind you, P, the point P is in, the point P is here, the point P is in u I0 and it is in y, so the point P belongs here, okay. So this is a non-empty open set, so it is irreducible, it is non-empty open in y, so it is irreducible. On the other hand it is also closed in u I0, so this becomes a irreducible closed subset of u I0, which under this isomorphism is going to be carried to phi I0 of y I0, which is well I have to give this some name, let me call it z I0, right, and so this isomorphism carries this irreducible closed subset into this irreducible closed subset, but then this is a variety here, okay, and so what is going to happen to so this isomorphism, so of course this diagram commutes, here also the diagram, there is no diagram here, I am going to draw it in the next board. So this isomorphism can also be, you can also write down what this isomorphism is, okay. So what this isomorphism is, well, let us write it down. It is going to be the following. So what is happening here, so let me write this part alone there. So I have O of an, which is A of an, which is k t1 tn, and I have this which is phi I0 star to O u0, which is SPN localized at xi0, take the degree 0 part, this is what it is. So this is just translation of this arrow into commutative algebra. Now we are going to do this. So you see when you go to an irreducible closed subset, the homogeneous coordinate ring is given by a quotient, because Sy is going to be given by Sy is a quotient of S of Pn, okay, and so you know so well maybe I will try to use this part of the board as well. Let me rub this so that I can extend this diagram to the right. So you know this Pn here, so there is ui naught sitting as an open subset of Pn, so this is an open subset, and that corresponds to this localization of S of Pn. So this is a this is a localization followed by well, so in fact this is sitting inside the localization as the degree 0 part, which comes as the localization of S of Pn. Okay, so this is the localization, this sitting inside the 0 part, and this part of the diagram corresponds to this. Okay, and what is happening is that y is an irreducible closed subset of Pn, and its homogeneous coordinate ring is a quotient of Pn. So what's happening is that you have here, you go mod Iy, you get S of y, this homogeneous coordinate ring of y. So this you know corresponds to this here, which is irreducible closed. A closed subset corresponds to a quotient. Okay, and so this corresponds to this, and then you know this thing, which is the intersection of y with this open ui naught, okay, that will correspond to something. What is that? It's going to be, well, it's going to be it's just you localize. So you know this is a very important property in commutative algebra, that localization commutes with taking quotients. Okay, localization is what is called localization is exact. Okay, the process of localization is exact. Okay, so localization transforms exact sequences to exact sequences, and you know a quotient fits into an exact sequence. So you take a quotient and then localize, is the same as localizing and then taking a quotient, and these are all since standard from a first course in commutative algebra. So if you go by that, so here is so what I can do is I can take Sy and I can localize it at xi naught. Okay, so this is the localization. All right, on the other hand, what I can do is I can on the other hand first localize at xi naught and then go mod Iy localize at xi naught. Okay, so this is not only can you localize a ring, you can also localize an ideal in the ring. In fact, you can localize a module. Okay, so Iy is an ideal there. Okay, and you can therefore localize it. Okay, this is the localization, and then so you know then here what you will get is just Sy localized at xi naught and the degree 0 part, which is again it will be a quotient here. Okay, and it is this quotient and this diagram commutes, and it's this quotient that corresponds to this irreducible closed set. Okay, so so this irreducible closed subset corresponds to this quotient, and this irreducible closed subset corresponds to this quotient. Okay, and on the other hand, what's going to happen on this side? On this side, Zi naught, which is phi naught of yi naught, is an irreducible closed subvariety of the affine space. So it's going to be given by its coordinate ring is going to be given by the coordinate ring of affine space modulo the ideal of Zi naught. Okay, so here it's going to be just here this irreducible closed here, this irreducible closed is going to correspond to a quotient here, and that quotient is just k, it is just going to be k t. So let me first write it as a and a of Zi naught. This is what it's going to be, and this is just this is just gotten by going mod ideal of Zi naught. Okay, and so which is just, so it's going to be identified with k t1 tn modulo ideal of Zi naught. Okay, and you're going to get an isomorphism like this. This diagram is going to commute, and this isomorphism is precisely the isomorphism of, it is just this isomorphism phi I naught that is carrying yi naught to zi naught. Okay, so this is what is going to happen. Now so you know the point, you see, if you take the point P is here, it goes to the point phi I naught of P, which is a point here, okay, and you know that because you have an isomorphism of isomorphism of these two varieties, the local ring of this at this point is going to be the same as the local ring of zi naught at phi I naught of P. Okay, so what you are going to get is, you are going to get local ring of yi naught at P is going to be isomorphic via phi I naught star to the local ring of Ez I naught at phi I naught of P. Okay, you are going to get this because we have seen that isomorphism of varieties is going to give rise to an isomorphism of local rings. But then you see, the local ring of yi naught at P is the same as the local ring of y at P, because yi naught is an open subset of y. Okay, because we have also seen that the local ring, to get the local ring at a point, you can restrict attention to an open subset which contains the point, and yi naught is an open subset of y which contains the point, because it is yi naught is just the intersection of y with this ambient open subset of the projective space. So this is, well, this is the same as, this guy is the same as OYP. Okay, this is what we want. We want to calculate this, and this is isomorphic to this, right? And what is this? See, this is this, as we have seen, this is the local ring at a point of an affine variety, and therefore it is given by, this is isomorphic to you take the affine coordinate ring of zi naught and localize at the maximal ideal corresponding to phi I naught of P. This is what we have already seen. We have seen this theorem the previous class, that previous lecture, that the local ring of at a point of an affine variety is just the affine coordinate ring localized at the maximal ideal corresponding to that point. So this local ring of zi naught at phi I naught of P is just the localization of the affine coordinate ring of zi naught, which is A zi naught, at the maximal ideal m of phi I naught of P corresponding to the point phi I naught of P. Okay, and of course, you know, this map is the localization. This is the localization map from the ring of coordinate functions to its localization, and similarly this will also be the localization map. It will be a localization map, and the question is that you need to know what localization map this is. So what is this going to be? This is going to be this ring Sy xi naught, okay, and then you have to further localize it. I mean, this is, take this degree 0 part, okay, and then further localize it at the maximal ideal that you get, which is the image of this maximal ideal here. Okay, so it's going to be localize it at phi I naught star inverse, so this, there's going to be a map like this, and that's going to pull back this maximal ideal phi I naught p, it's localizing, you have to localize at this ideal, okay, this is what it is going to be, alright. If you just follow the commutative algebra, this is what it's going to be, and you have to show that this thing, is the same as that, okay, you have to show that this is the same as that, right. Yeah, so so one has to really write this down. So let me do the following thing. So you have this projective space, and you have this y, and you have this point p, okay. Suppose p, of course p is in u I naught, okay. So you know this p has homogeneous coordinates lambda naught blah 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 lambda n, okay, and lambda, you know, lambda I naught is not 0, okay, because it is in u I naught. And now you look at this projective space as a quotient of the affine space above, I mean the punctured affine space above, and then the inverse image of p will be just the line in affine space through the point lambda naught lambda n minus the origin, okay, this is what you are going to get. And you see, what is the equation of this line, in the affine space, okay. So you see the picture is that, you know, you have something like this, you have the origin, and then you have this line L, okay, which is this line L, and of course there is a point on it which is given by lambda naught etc lambda n, and any other point on it is given by t lambda naught etc t lambda n. That is how any other point on this line is given by, and therefore if you look at the ideal of functions that vanish on this line, it will be a homogeneous ideal, okay. We have already seen that whenever a polynomial vanishes on a line, it has to have no constant term, and then every homogeneous component of that polynomial also has to vanish on that line. So the ideal of this line is simply gotten by eliminating t from the equation of a general point on this line. So this line is given by, you know, xi is equal to t lambda I, okay, this is how it's given, where t is a parameter, okay, and if you eliminate t, you will be writing xi by lambda I is equal to t is equal to xj by lambda j, but then you cross multiply it because some lambda I or lambda j may be 0. So you will get that the ideal of this line in affine space of polynomials that vanish on this line is just the ideal generated by xi lambda j minus xj lambda I. It is just this ideal, okay, it is just this ideal, and you know, this ideal will also be the ideal, the homogeneous ideal of the point the image of this ideal. First of all, this ideal will be a homogeneous ideal, of course, because it is generated by all these elements which are all homogeneous of degree 1, okay, and what is the zero set of this homogeneous ideal in projective space? It is just this point, okay. So this will also be equal to the ideal of the point in projective space, okay, and therefore so this ideal corresponds to this point in projective space, and you know, what will it correspond to as a point of y? It will correspond to the image of this ideal in sy, okay. So you see this ideal is here, alright, it is a homogeneous ideal here, and if you take its image here it will correspond to the point p considered as a point of sy. In other words, I am saying if you take the image of this ideal here, you will get exactly m of p, namely the ideal generated by all homogeneous functions, homogeneous polynomials which vanish at the point p, okay. So I am just saying that this is the same as m of p inside its quotient is m of p. So so this sits inside Sy inside S of Pn, and then you have a quotient which is S of y, and its image there will be just M of P. Okay, this is what you will get. So this is what M of P is. All right, it's just the image, it's just the quotient of this ideal. Okay, mind you, this ideal will contain this ideal will contain the ideal of y. Okay, this will contain I of y. Okay, and that is the reason why mod Iy it also defines an ideal. All right, and it corresponds to the point P in y. All right, now so you know, if you go and try to calculate what this quantity is, this quantity is just, so you know, Sy localized at MP0 is going to be you know, you see what I am doing is I am taking a quotient, okay, I am taking quotient by an ideal, and then I am localizing. All right, but I already told you that localization commutes with quotients. So what you can do is, this is the same as you take the SPn, okay, localize it with respect to that ideal, the ideal generated by xi lambda j minus xj lambda I, okay, and then what you do is you localize at this and then go mod that's right, you go I of y localized at this ideal. And then take the degree 0 part. Okay, this is what it is, right? But then the trick is that, you know, the point is the following. The point is that, you know, since the point lies in u I naught, this lambda I naught is non-zero. Lambda I naught is non-zero. Let me write it down. So the point here is lambda naught lambda n, okay, with homogeneous coordinates. That is going to the point here, which is going to be lambda naught by lambda I naught lambda n by lambda I naught. That is going to be the point here. Okay, therefore if you look at this calculation, you will see that the maximal ideal corresponding to this point is going to be the maximal ideal of phi I naught of P is going to be just T1 minus lambda naught by lambda I naught and so on, Tn minus lambda naught by lambda I naught. Of course I omit lambda I naught by lambda I naught. Okay, it is this ideal mod, this is this ideal mod ideal of z naught, z I naught. This is what the maximal ideal here is. Okay, it is a maximal ideal of this point. The maximal ideal of this point is just the maximal ideal of this point in the affine space modulo this ideal of z I naught. Okay, so this point, you see this point corresponds to a point in affine space, so it corresponds to a maximal ideal here. That maximal ideal is this, okay, and that maximal ideal mod I of z I naught will give me the maximal ideal in a z I naught to which the point corresponds to in z I naught. Okay, so this is what it is. All right, and you know, if I take each of these elements like T1 minus lambda naught by lambda I naught, okay, if I take any such element and if I take its image under this phi I naught star, a map induced by phi I naught star, what I will get is, you know what this map is, this map is just homogenized with respect to x I naught, okay. So what I will get is, I will get you know I will simply get x naught by x I naught minus lambda naught by lambda I naught, okay. This is what I will get when I apply this map. I am supposed to homogenize it with respect to x I naught and then divide out by the same power of x I naught, okay. So this is what I will get, and this is clearly an element of and similarly, you know, if you take the element Tn minus lambda naught by sorry, this is this should be lambda n, Tn minus lambda n by lambda I naught, that will go to under this phi I naught star, it is going to go to x n by x I naught minus lambda n by lambda I naught. This is what it is going to go to, because after all the map from here to here is, you just send f to homogenization of f divided by and then you remove this power of xi that you put to homogenize it, okay. So if you apply this, this is what you will get. Therefore what this calculation tells you is that it tells you that this ideal, okay, is actually it is, no, xi naught xi naught by xi, x naught by xi naught is degree 0 and lambda naught by lambda I naught is also degree 0. This is a difference of 2 degree 0 elements, so it is degree 0. It certainly x naught by xi naught is certainly in the degree 0 part of this, okay. So you know, if you do this, what you will get is you see all these elements are here, these elements they are all here, okay, and these elements generate a maximal ideal and it's localized, and that maximal ideal is precisely this maximal ideal, okay, at which you have to localize this to get O y I naught p. So you know, so phi I naught star inverse of m of phi I naught of p is actually the ideal generated by all these guys, x naught by x I naught minus lambda naught by lambda I naught dot 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 xn by xi naught minus lambda n by lambda I naught. Of course, you know, I am able to write all this because lambda I naught is non-zero, that is why I can write all this, and therefore this this ring, what you get is just so O y I naught comma p is just sy localize at x I naught, take the degree 0 part and further localize at this guy x naught by x I naught minus lambda naught by lambda I naught and so on, xn minus by x I naught minus lambda n by lambda I naught. This is what it is. So let me write this. So let me again rewrite this. What I am getting here is, this is sy localized at mp. mp is just the is this ideal mod iy, okay. So it is just sy this ideal generated by xi lambda j minus xj lambda I mod iy then localized at 0, okay. But you see what I want you to understand is that these two are the same. You see what I have done here is I have taken sy, I have inverted xi naught, okay, then I have taken the degree 0 part and then I am inverting everything outside this, okay. But then you know, if you think of it naively, think of this xi naught as going out and getting multiplied with this, okay. See, if you already inverted xi naught, okay, and you want to do this, okay, it's the same as multiplying this thing throughout by xi naught. So what I want to say is that this is the same as sy localized at this and then take the degree 0 part, which is exactly that, okay. So I am claiming that these two are the same, okay. You have to just satisfy yourself that that is true. Purely, it's a purely commutative algebraic thing. See, what you must understand is in sy localized at xi naught, you know, xi naught is a unit, mind you, xi naught is invertible. Therefore, you know, to localize this here, it's just enough to localize this at x naught minus, you can multiply everything by xi naught, okay, because xi naught is after all a unit. So it's enough to localize this at x, instead of localizing it at this ideal, it's enough to localize it at x naught minus xi naught times lambda naught by lambda I naught, that is, you can multiply by xi naught throughout, okay. But then localizing, but you know, x naught minus xi naught lambda naught by lambda I naught is the same as up to a multiple of lambda I naught, it is just x naught lambda I naught minus lambda naught x I naught, which is of this form. So these two are one and the same, okay. So let me maybe continue here and say that you know, so let me erase this line and write that this guy here is, you know, it's sy xi naught localized at 0 and then further localized at, see, now I am going to multiply throughout by xi naught because xi naught is a unit, alright. So it will become x naught, so in fact I can also multiply by lambda I naught because lambda I naught is also a non-zero element, so I multiply throughout by lambda I naught xi naught. So what I will get is I will get x naught lambda I naught minus lambda naught xi naught blah blah blah, and then I will get xn lambda I naught minus lambda n xi naught. I will get this. So the way to do it is you remove the 0 here, then you take the 0, okay, you can do this. So I'll leave it to you to check that, you know, this guy here and this guy here are one and the same, okay. It's just a matter of some commutative algebra, okay, to check that this is the same as this, okay. It's an easy check. You'll have to check whether this is also equal to this, alright, but I leave it to you to check that this is equal to this, okay, and I'll stop here.